So now I will calculate the mass defect, which would be equal to the mass of the proton multiplied by the number of protons, and then I'd say that the mass plus the mass of the neutrons multiplied the number of neutrons. So I'll subtract that the actual Sn, which is the total mass. So from there I can say that the number of protons I have found there is already 50. So I have 50 and then multiply by the mass number of a proton, which I believe it remains almost constant at 1.007825 unit mass, and then plus the number of neutrons, which is the ones we found calculated to be 70, multiplied by the mass number of a neutron, the mass of a neutron, which is 1.00866 U, and then minus that mass now that we are given here in form of U, which is 119.902197 U. So let me see, what do I get? So I have 50 multiplied by 1.007825 plus 70 multiplied by 1.00866 and then minus 119.9021, and then I get the 1.095603 U. So that is the mass that I get there. So now from here I can calculate the binding energy, because I know that the binding energy will actually be equal to the mass defect multiplied by the speed of light, and then I know that the speed of light squared is the same as 931.5 mega electron volts per U, and then now my binding energy will actually be equal to what I got, which is 1.095603 U multiplied by 931.5 mega electron volts per U. So now I get that the binding energy will actually be times 931.5. Then I can see that here the U will actually cancel U, and then I'm left with 1020.55 mega electron volt. And then if you want to convert it to joules, obviously 1 electron volt is equal to some number of joules, but then I prefer to just leave it here as mega electron volts. That one is clear, ne? So now they are saying also what is the binding energy per nucleon. So to calculate the binding energy per nucleon, so for part B, the binding energy per nucleon will actually be the binding energy divided by atomic mass, and then that was 1020.55 mega electron volts divided by, now the mass, the total mass, that was 120 there, and then that means we're just gonna divide this by 120, because obviously they are saying per nucleon, so we have 120 nucleons actually, because a nucleon, if I'm not mistaken, nucleon is equal to protons plus is actually the total protons plus neutrons. I don't know if my spellings are fine. So that should be per nucleon now. So if we divide that by 120, I get 8.5046 mega electron volts per nucleon. Is it clear, Mr.? That was what I'm trying to explain here. So if we have this element here, and then we have A here, we have Z here, and then we have N here. So A is actually the Z plus N, right? So these are actually A is actually the nucleons. So exactly, it's protons plus neutrons. Yes. So that means is that 120 is equal to that 70 plus 50 there. So yeah, that's why we divide then by this, because we have 120 neutrons. Exactly. Hmm? But should not be found. Should have some. Yeah, that 50 was also confusing me at first. I'm trying to check something and here. Abana nemfati la uthi ndiliqeleko bhuti. Uyayibona loo nto uba bendingeloxeleko bendingazumdinga vele. So now Minier, we can actually go to the second question. If then we agree on that one, on the way we did that one. So let me just say snipping again. Or I can just say control copy. And then I put the new one. Control V. Then I come here. This thing is hiding me here. I don't know how to remove it. Okay, it's fine. So now for this one, we are given that an alpha particle has taken part in the following steps. So the first one, proton is first removed. So number one, remove proton. And then number two, it says that number one is this one, you're removing the proton. Number two, it says that then a neutron is removed. So number two, remove a neutron. And then number three, the remaining protons and neutrons are separated. separate a proton and a neutron. So determine the energy required for each step. So we want the energy. What is the energy that is required? Energy required for each step. Yavakala Mosmist. So we just want the energy that is required for each step. So I will go to the other questions. And then what we are given that the atomic and neutron masses are these. So we are given these here. So now if we go here, we have our helium 4H, we have 4He, and then we are given that 4.002603U. In fact, even if I don't rewrite them, since they're already there, I'll just start to solve here. So I'll make this to be a solution. So now here we're given that helium is 4.002603, and then the helium 4 and then helium 3 is that one. We are given H3, we are given H2, we are given H1, and then we are given the neutron. So we want the energy. So now the way I think we're supposed to do it is that now we have a helium. We actually having this helium, right? And then this helium is actually 4, and then 2, and then we have 2, which is equal to which would be equal to 3, 1, and then H2, because we remove one proton there. So if we remove one proton, again we said this one represents protons. You see this one, obviously we left with this one. And then if we have removed that proton, obviously the nucleons will be affected, because remember we said that nucleons are equal to protons plus the neutrons. So since there were 4, there will now be 3. You get that, right? Exactly. So also these ones, they are it's neutrons which will remain the same. So obviously the 2 plus 1 here, 2, and the 1 will be that 3. So it makes sense because we only removed a proton. And then now we'll say that plus the one that we have removed. So it's 1, and then here obviously we'll be left with 1, so that when you add this one and that one will give us that 2. So obviously this side, I believe that should be 0. So that's what we have. That's what I think it work, because if you remember when we multiply from this other formula, when we calculate the binding energy, instead of saying protons, you multiply by the mass of a hydrogen atom. Do you remember that? It was in this other slide. Let me just check. Let me open a new one here. So I believe that with what I see now, to me I'd say that the proton actually is related to a hydrogen atom. So hence we use those hydrogen rather. So let me check. Yes. So let's check here. Let's check here. I want that I think this one is very far. Because there's this specific formula that I need. Exactly that specific one. So let's check this one. Oh, that maths. Yeah, everything went well, Yasmin. Yeah. They were behaving. They were behaving. You know me, mister. I tell them. If you think you are clever, I won't mark your test. I mean, angezelwa Jimenez. Yeah, angezelwa. No, trust me. So can you see this formula? You see, yeah, this is. You see, instead of saying Z multiplied by mass of proton, they're saying Z multiplied by mass of hydrogen atom. And if you remember, Z is a proton, is number of protons, right? Multiplied by the mass of a hydrogen atom. Instead of saying number of protons multiplied by the mass of what? Of a exactly. Instead of saying multiply by mass of a proton. That's why I'm saying it might happen is because that the mass of the proton and then the and hydrogen atom, they're actually similar somehow. But you get what I'm trying to say, right? Because this mass of a hydrogen atom is actually in a place where we're supposed to say MP, the mass of a proton. Yeah, so that's what I think.
Hydrogen has only one proton, and it is used as reference for other atoms. Hence, even the studies are done with hydrogen and link them to other atoms because of the relativity.
Okay. So that means protons is related to hydrogen atom with regard to that.
Hence, we relate the protons of other atoms because
With the hydrogen atom.
hydrogen atom only has one atom.
Yes,
I mean,
one
only
proton and one
proton
electron.
and one
Yes.
electron.
Yes.
And when doing study of other atoms, the periodic table, always reference to hydrogen. Hence, hydrogen is said to be not having distinct characteristics.
Answer the explanation, man.
You unmuted.
We need chemical engineers. So you see. Yeah. So kuthiwa hydrogen apparently has one proton, right? So other atoms are then referenced with regard to the hydrogen because hydrogen has one proton and one electron, because it's actually H plus like that. So obviously, yeah. Uh, chemistry person, does hydrogen as a neutron? Let's make sense out of it. Let's make sense out of it, mister. Because if we can say H, ne, we have one proton, ne? We have actually okay. We have one proton which is Z here, right? And then we said we have one electron indeed. So now the question is is with what? With a neutron? Because atomic mass, maybe it doesn't, because I think atomic mass of a hydrogen is 1. Am I right? So we can confirm that it doesn't have, because now if we subtract, if we say A is equal to Z plus N, and then we know that N will be equal to A minus Z, that means we get a 0. Yes. So it makes sense to just take the mass of that hydrogen as it is. So now, let me use the black here. So now after this helium, so we can have to calculate what? The mass that is needed, ne? Mass needed to remove a proton, ne? What it missed? So we need the mass that is needed, I mean the energy needed to remove a proton. Yes. Yes, exactly. Number one. Yeah. So in an actual note, that is the binding energy needed to remove that thing. So we know that the mass defect, I'm doing now. So we know that the mass defect will actually be, remember we said that if we have a nucleus, right, that consists of a proton plus neutrons, is actually light, ne? It's lighter than when we have a protons plus a neutron separated. If we weigh this and then we weigh this, so this is heavier. Exactly. Yes. So if we do that subtraction there already, we get the mass that is gonna be needed for binding energy. Because we said that mass will be converted to binding energy. So that means to get that mass defect, the biggest mass minus the total one, which means we take these 3 1 H2 plus 1 1 H0, which are the ones separated there here, right? And then now in an actual note, let me just say specify that these are masses. So we take the mass of H3 plus the mass of H1, right? And then we subtract now the mass of that what? Of that full nucleus, because we know that one is what? Is lighter, right? That mass defect, because again we know that this will give us a bigger mass than this one. So let's do and see. So now if we take that mass here for a hydrogen, we're coming back to the information we are given. We're told that for one hydrogen here below is actually the 1.007825. So we have 1.007. Okay, it's actually 3. I started with 3, but either way you understand. This one is for the 1. Because either way is addition. And then for 3, for the 3 ones are already given also here. Can you see that one? So for 3 hydrogens are already given, that is 3.01049. So we have 3.016049 16049 U, and then we subtract the mass of the total one. I carry the actual helium is the one here above. the full nucleus is this one. Can you see that, Menier? It's this one. So that's 4.002603. 4.002603. So now let me subtract that and see what I get. 1.007825 plus 3.016049 and then minus 4.002603, and then I get 0.021271, and then those are measured in unit mass. And then now we can find our binding energy. We know that our binding energy is actually mass defect multiplied by the speed of light squared, and then we know that 0.021271 U multiplied by 931.5 mega electron volt per U, and then see what do I got. I get 931.5, and then I get here 19.81 mega electron volt. So 19.81 mega electron volt. So this is the answer that I get, say. To remove that proton. That one proton. So first thing we said, we have a total atom, and then this total atom, we remove what? We remove one proton, and then we are left with 3. So in an actual note, that atom is equal to this plus this. So obviously, to remove that one, we need to have these 2. And then we know that the mass of these 2 is bigger than the mass of that one. So if we make this different, and that difference will give us the energy that was needed to actually split that thing into one hydrogen atom and that guy there that is left. I think it makes sense that way. So now they are saying in the second question, now to remove what? A neutron. Now let's go back. So after removing the hydrogen atom here, notice what we are left with. After removing that, we are left with this guy, right? So exactly. So now when we are left this guy, we again remove a neutron from this guy, not from the start, because the question says then, you see, then remove a neutron, you see. It doesn't say from the full helium, again start afresh and remove a what? A neutron. We put that proton back. We have removed a protons, now we remove a neutron. So now if you go back here, after removing that proton, we are left with what? With this 312H. So we are left with this 312H. Now we again want to remove what? Now again a neutron. So when we remove a neutron, we will be left with something like this. So now we want to remove one neutron. And then of course we already know that whatever we remove, either proton or neutron, we know that this guy will change. It will affect the total mass, isn't it, Menier? So if that will change, exactly, that means we'll be left with 2 here. And then since we are removing a neutron, we are going to affect these 2 now. That means we're going to be left 1 here. Does it make sense? Yes, it does. And then now, what about this guy now here? This guy remains the same because we have already removed, there were 2. This remains 1 still. So obviously plus, and then here that should be 1 in order for us to say 1 plus 1 is 3. And then this should just be 0, and then this should be 1. because I mean, we're just balancing. I mean, this guy plus this guy will give us this 3, and then this 0 plus this one will give us 1. This one plus this one will give us 2. Does it make sense? Yes, it does. So yeah. Oh, it's gonna, before it switches on, the Wi-Fi is gonna switch off first, ne? After 10 minutes. Okay, let's just leave it here, maybe. But obviously from here, the only thing that we're gonna do, we're gonna say mass of this minus the mass of this. That will give us the mass defect, and then we again multiply by c squared. It gives us the binding energy. Yes, but now obviously taking into consideration these ones, that we are left with 2, and then here we are left with 1. But obviously no problem. Maybe we'll continue after, then when the Wi-Fi is back on your side. Sharp.